Welcome to an introduction to remote sensing. In this lesson, we're going to review three major concepts behind remote sensing, which are reflectance, spectral signatures, and spectral resolution. So here's your typical elementary school representation of the world. We have the sun, we have a little pond, we have some grass, and we have a house. And here's some solar radiation coming down. Except that this solar radiation is actually in the form of photons, represented by these little dots, that travel in waves. And as we can see, different photons have different wavelengths. That is, the distance between waves is different. So for instance, photons in the red region would have a larger wavelength, or a larger distance between waves, than photons in the purple region. And we can see that here. Except that we don't just have three photons, but a nearly unlimited number of photons interacting with materials on the Earth's surface every second. And some of these photons, like this red photon, are absorbed by the materials they interact with, while other photons, like this red photon, are reflected and bounce off of the materials they interact with. So this is happening constantly for photons of all different wavelengths, and some of these photons are being reflected, while others are being absorbed. And when we take a lot of photons hitting a surface, we can compute the reflectance value for a given surface. Let's say for the roof of the house. And the reflectance value equals the number of photons that are reflected or bounce off a surface over the number of photons that are incident to the surface. So in this case, if 2 out of every 3 photons are reflected, the reflectance value is 2/3, or 66%, since 66% of the photons that are hitting the roof of the house are reflected. And each material will have a given reflectance value for a given wavelength. For example, we might say that for photons in the red region, the reflectance value for the roof is 66%, whereas the reflectance for the grass might be 10%, since only 10% of photons in the red region are reflected, and the other 90% are absorbed. And this actually ends up being pretty important, since the reason that we perceive the roof as red is because it's reflecting a higher percentage of photons with wavelengths in the red region. And we can see this if we examine the plot of wavelength versus reflectance for the red roof. So wavelength is plotted on the x-axis, and reflectance is plotted on the y-axis, and expressed as a percent. And we can see that for photons with wavelengths in the blue and green regions, with between 400 and 600 nanometers between waves, reflectance is relatively low. That is, a relatively low percentage of photons in these wavelengths are reflected by the red roof. But if we examine photons with wavelengths in the red region, between 600 and 700 nanometers, we can see that a much higher percentage of these photons are reflected, which is why we perceive the roof as red. And this plot of reflectance values for a given material, in this case for the roof of the house, across different wavelengths, is known as the material's spectral signature. So this is the spectral signature for the red roof, and you can see it even looks a bit like a signature. But it turns out that the wavelengths that we can see, or those between 400 and 700 nanometers, in what we call visible light, make up just a tiny fraction of the greater electromagnetic spectrum. So this means that in reality we have many, many more photons that are interacting with materials on the Earth's surface. And although we can't detect photons in these wavelengths, some satellites are able to detect photons in these wavelengths. Since the satellite knows roughly how many photons of a given wavelength, let's say in the red region, are being emitted by the sun, and it can measure the amount of photons of a given wavelength that are being reflected back to the satellite, it's possible for the satellite to make an estimate of a material's reflectance for a given wavelength. So for instance, the reflectance of the roof for photons with wavelengths in the red region. So let's look at the spectral signature of the red roof, as measured by the satellite. As you can see, this satellite is picking up the reflectance values for the wavelengths in the visible region, from the blue region to the red region. But the satellite is also picking up reflectance values for the house in a range with wavelengths just outside the range of human detection, in a zone called the near infrared, with wavelengths that are slightly larger than those in the red region. Now it turns out that in most cases, a sensor aboard a satellite will only be able to measure small parts of the electromagnetic spectrum. So a given sensor might measure part of the blue region, part of the green region, part of the red region, and finally part of the infrared region. And each of the areas that is measured by a sensor is called a spectral band. So in this case, we would have 4 spectral bands, representing 4 different parts of the electromagnetic spectrum. And the number of bands and the width of these different bands is known as the satellite's spectral resolution. For each band, the sensor will take an average reflectance value for the wavelengths measured in that particular band. So instead of a line, the result from a sensor for the spectral signature of the red roof might look like this. So now instead of a squiggly line, we have 4 dots representing the average reflectance values of the red roof for different bands. But let's return to our squiggly line for a second that represents the spectral signature of the red roof over every wavelength. So we can see that for the blue region, the green region, and the near infrared region, the reflectance values stay pretty consistent. So our bands did a pretty good job of averaging the reflectance values for these regions. But for wavelengths in the red region, reflectance values change a lot from the beginning of the red region to the other end of wavelengths in the red region. So our reflectance value would change a lot if we moved our band from here to, let's say, here. So it's important to remember that just because a band corresponds to wavelengths in a certain region of the electromagnetic spectrum, say the red region, doesn't mean the reflectance value given by a band represents the reflectance value for the entire region. Instead, the reflectance value for a band only correlates to the average reflectance value for the wavelengths measured by that band. So for example, in the case of this band, the black dot, or reflectance value, would represent the average reflectance for wavelengths from about 710 nanometers to 730 nanometers. So we return to our elementary school world. We can see that as the satellite passes overhead, it will pick up reflectance values for each of the materials it passes over, for each of the bands that it's measuring. So in our case, with 4 spectral bands, the satellite will pick up 4 reflectance values for the roof as it passes over the roof, 4 for the grass as it passes over the grass, and 4 for the water as it passes over the water. And this is what that looks like if we plot up the spectral signatures of these 3 different materials. And let's add some lines between dots to help us visualize this. So as we saw before, the red roof, symbolized by the red dots, is relatively low in the blue and green regions, and then has higher reflectance values for the red and near infrared regions. And if we look at the spectral signature for water, we can see that reflectance values are pretty low for each of the 4 bands, but that the highest reflectance value is in the blue region. And this helps explain why we perceive water as blue. And finally, if we examine the spectral signature for grass, we see that reflectance is pretty low in the blue and the red regions, but that spikes in the green region, which is why grass is perceived as green. And then finally we see this big spike in reflectance for wavelengths in this part of the near infrared zone. And we'll take away the connecting lines. So which band do you think would be most useful in distinguishing water, as represented by the blue dots, from the red roof, as represented by the red dots? Well, in bands 1 and 2, it looks like the reflectance values for water and the red roof are pretty close together. So it might be hard to tell if it was water or a red roof reflecting photons in these wavelengths. But in bands 3 and 4, the reflectance values for water and the red roof are pretty different. So you might be able to say, well, if a material is absorbing most of the photons with wavelengths around 800 nanometers, and reflectance is low, it has to be water, because water is the only material with reflectance values this low for these wavelengths. And in the next series of videos, we're going to start getting at the idea of how we can use these differences in reflectance values to distinguish between different materials on the Earth's surface. So I hope you'll join me for that, and thanks for listening in.